All right, today's lecture is over section 3.5, rational functions. So let's look at the definition of rational function. We start with f of x is equal to p of x over q of x. So p is going to be the normal notation for the numerator, q is going to be the normal notation for the denominator, and for it to technically be a rational function, we need the p of x and the q of x to be polynomials. So basically, a rational function is a polynomial divided by another polynomial. One important aspect of rational functions is the domain. So the domain of the rational function f of x, the domain is the set where q of x is not equal to 0. And this simply comes from the fact that you cannot plug in a value for x that would make the denominator 0. You cannot divide by 0. So let's look at some examples, and we've done these before. This is just review. Example 1, find the domain. F of x is equal to 3x minus 1 over x plus 5. The domain of a rational function is the set where the denominator is not 0. So the trick to solving this is to set the denominator equal to 0, solve for x, and you get x is equal to negative 5. And then that is the bad point. That's the point that has to be excluded. If you remember, we drew this on a number line, and we said, all right, here's the bad point, and you'll put all the bad points on this number line with an open circle. And then you write the domain as the union of intervals. I encourage you to write out the number line because you can explicitly see how many intervals you should end up with. You need an interval here on the left that is from negative infinity to negative 5, union. You need an interval on the right side that is negative 5 to infinity. And you can also remember there were other notations that you could use, set builder notation and etc. Here we'll just use interval notation. Example B, g of x is equal to x over x squared minus 3x minus 10. Set the denominator equal to 0. So we have x squared minus 3x minus 10 equals 0. You have to solve whenever the denominator is equal to 0 in some fashion. This one is a quadratic, so you have several ways of solving quadratics. You can either factor, complete the square, or use the quadratic formula. Here I'm going to factor. This is going to be 5 and 2. We need to make negative 3 in the middle. So the 5 is going to be negative, and the 2 is going to be positive. And then when you set each of these factors equal to 0, you get x is equal to negative 2, and x is equal to positive 5. Draw the number line. Place both numbers on the number line in order. And then create those intervals around those points. So the first interval is negative infinity to negative 2, union, negative 2 to 5, union, 5 to infinity. Let's look at example C. j of x is equal to 8x squared minus 1 over x squared plus 9. You want to find the domain. So you set the denominator equal to 0. X squared plus 9 equals 0. To solve this, since there's only one x variable here, I'll move the number to the right side. And we have x squared is equal to negative 9. You can't square a real number and get a negative answer. You could only do that with the i's and the complex numbers. We're only dealing with real numbers in this scenario, so this has no solution. Because it has no solution, that means there are no bad points that have to be taken out of the domain, and so the domain is all real numbers. Negative infinity to infinity. All right, let's look at page 2. And we need to show you some notation for dealing with how x approaches certain numbers. The first piece of notation is x approaches c, and then you'll notice a superscript of a positive sign. That means x approaches c from the right side. So this is x approaches c from the right, and it's the right side of c. So basically, if you're looking, here's where x is equal to c, you're going to be looking at the function as it comes in from the right side and gets closer and closer to c. Now there is one other part to this, and it's that x is not equal to c. When you say x is approaching c from the right, you never really consider that x could be equal to the number that you get to. The next notation is very similar, and you can probably guess what this means. This is x approaches c from the left. And again, x is not equal to c. And this would be approaching c from the left. The last two involve infinities, and we've already seen this notation when we talked about in behavior. This is the alternative form of the in behavior notation. The first one means x approaches infinity, which means it increases without bound. And when you say that something is increasing without bound, basically what you're saying is that it's just getting larger and larger and larger, and there is no limit to how high the x values are going to go. The last one, of course, is x approaches negative infinity, and that means the x values are decreasing without bound. The x values are getting smaller and smaller and smaller, and there is no limit on the bottom as well. Again, these we used before when we talked about in behavior. X goes to negative infinity is on the left, x goes to positive infinity is on the right. The first two, x goes to c from the left or right, is going to be some sort of interior number where the x's are going to. Let's take a look at example 2 and see how to use all this. Example 2 says, let f of x equal 1 over x. And then here's the graph of 1 over x. Question A, as x approaches 0 from the right, what are the f of x values approaching? So if I sort of trace out the graph when x is approaching 0 from the right side. You can see the behavior of the y values. The y values are increasing, and there's an arrow, so they never stop. So the f of x values are approaching infinity. And that's simply because these y values, remember f of x and y are the same thing, the y values are increasing without bound. They just keep going higher and higher and higher as you get closer and closer to 0 on the x-axis. What about question B? As x approaches 0 from the left, what do the y values do? So coming in towards 0 from the left, we see that these y values are decreasing without bound. They just keep going. And so they would be approaching negative infinity. Questions C and D are about the end behavior of this graph. As x approaches infinity, what do the y values approach? So here I'm going to trace out the right end behavior, x going to infinity. And you can see that the further and further we go out, the closer and closer the y values get to 0. They get very close to the x-axis here. And the same thing on the left. As x goes to negative infinity, the y values get closer and closer to 0. Let's take a look at page 3 and vertical asymptotes. The line x equals c is a vertical asymptote of the graph of a function f of x if f of x approaches infinity or negative infinity as x approaches c from either side. Okay? So you have 4 graphs. Let's draw this first one with an x value of c. Vertical asymptotes are normally represented on the graph by a dashed line. And of course, it's a vertical line. So one scenario is that the f of x values could approach positive infinity as the function approaches c, as the x approaches c from the left side. So as x goes to c from the left, the y values approach positive infinity. They just keep rising without bound. Also from the left side, the function values could go down to negative infinity. On the right side of c, you could have a function that approaches positive infinity or negative infinity. Usually you'll have a mixture of these two, coming in from the left, coming in from the right, and of course you have all 4 combinations. So how do you find the vertical asymptotes of a rational function? 2 steps. First, you need to reduce the rational function to lowest terms. Usually you're given the function in lowest terms, but you do need to check to make sure that you have that in lowest terms. We'll even show you one that is not in lowest terms so you can see what that looks like. And then number 2, solve for q of x when it's equal to 0. This is the same process as finding the domain. So the vertical asymptotes are in part elements that are not in the domain. There's another part of numbers that are not in the domain that are not vertical asymptotes, and I'll show you that as well. Example 3. Find the vertical asymptotes of f of x is equal to 5 over x plus 3. So this one is reduced. Nothing can cancel. Step 2, set the denominator equal to 0. Solve for x. And that's your vertical asymptote. It's even in the right form. It's x equals a number. That's the equation of a vertical line. So that's your vertical asymptote. Example 4. Find the vertical asymptotes of m of x is equal to x plus 9 over x squared minus 81. This one needs to be reduced. So I'm going to rewrite it as x plus 9, and then the bottom factors as x plus 9 times x minus 9. That, of course, is called the difference of two squares. Notice that you have the same factor in the numerator as in the denominator. When you have that, they cancel. And that leaves us with, there's nothing left on top, but we need a placeholder, so we're going to put a 1. And then the denominator had x minus 9. You take this reduced form of the rational function, set the denominator equal to 0, you get x equals 9, and that is your vertical asymptote. Now notice that the canceled factor is also a number that is not in the domain. So this x plus 9 from what we canceled would give you x equals negative 9. Negative 9 is not in the domain, but it is also not a vertical asymptote. It's actually called a hole. Because the graph, when you get close to x equals negative 9, is actually one of these little holes that you've seen in your homeworks and in some other examples. It's a hole in the graph, and then the graph keeps going. Let's look at example 5. Find the vertical asymptotes of p of x is equal to x minus 7 over 2x squared plus 5x plus 2. Same procedure as before. You see if you can reduce anything. This one is reduced already. Take the denominator. Set it equal to 0. This one factors as 2x plus 1 and x plus 2. Set each factor equal to 0. Solve for x. And you get x is equal to negative 1/2 and x is equal to negative 2. These are your vertical asymptotes. Now later on in the lesson, we will be using the vertical asymptotes to help us graph each of these rational functions. So you'll see the dashed lines when we put all of this together, all the parts of today's lesson, toward the end of class. Next, let's look at horizontal asymptotes. A horizontal asymptote, that is the line y equals d, is a horizontal asymptote of the graph of the function f of x. If f of x approaches d as x approaches infinity or negative infinity. It is essentially the end behavior of a rational function. Of course, horizontal asymptotes are going to be horizontal lines. And you have these four types. Here's y equals d and the horizontal asymptote at d, and it can come in from above and level off to where y is equal to d. It could come in from below and those first two are the left in behavior. What about the right in behavior? Could come in from above, or it could come in from below. How do you find the horizontal asymptote of a rational function? There are three criteria. Starting with your rational function, where p is the numerator and q is the denominator, you check the degrees of the numerator and the denominator. So step one says, if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is automatically y equals 0, period. So if the top, and we're looking at the degrees, if the top is smaller than the bottom, then it's y equals 0. Number two, if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is a horizontal line in the form y equals the lead coefficient of the numerator divided by the lead coefficient of the denominator. Okay, so LC stands for lead coefficient. And if that doesn't happen, finally, number three, if the degree of p of x is greater than the degree of q of x, so if the degree of the numerator is larger than the degree of the denominator, then you do not get a horizontal asymptote, but you will get some other type of asymptote. In this class, we usually do the slant asymptote, and this occurs when the degree of p of x is equal to the degree of q of x plus 1. So the numerator has a larger degree, but you get a slant asymptote when it's just 1 degree bigger. And of course slant asymptote is going to mean some sort of line that's been slanted. It is true that if you have a degree that is 2 bigger in the numerator, then you get a parabolic asymptote because it's degree 2 larger than the denominator. Rational functions only have one horizontal asymptote. There are functions that can have a horizontal asymptote on the left and a different one on the right. Because horizontal asymptotes are the in behavior, there's only these two. You can only have a left one and a right one. All right, let's take a look at example 6. Now keep this chart handy so that you can refer back to it. Example 6 says, find the horizontal asymptote of f of x is equal to x plus 4 over x squared minus 3x plus 8. To determine the horizontal asymptote, you look at the degrees of each of these. So what is the degree of the numerator? That would be 1, because we have x to the first, and the 1 is the highest power of the exponent in the numerator. Determine the degree of the denominator. The highest power in the denominator is 2 because of the x squared. When the degree of the numerator is smaller than the degree of the denominator, your horizontal asymptote is automatically y equals 0. Let's look at example 7. Find the horizontal asymptote of f of x is equal to 3x squared minus 3x minus 4 over 8x squared plus 9x plus 1. You want to compare the degrees of the numerator and the denominator. So the degree of the numerator is 2. That is the highest power of the x in the numerator. And then you want to look at the denominator, and the degree in the denominator is also 2. When the degrees are equal, the horizontal asymptote is a line in the form of y equals the ratio of the lead coefficients. So this horizontal asymptote is y equals 3/8. Now remember, these lead coefficients come from the degree giving term. You have to have everything lined up properly in order to find those terms. It happens that it is x squared and then the x and then the constant. So just circling the first numbers you see may not give you the right answer. You have to make sure that everything's lined up properly first, and then it will absolutely work. And of course, this was rule number 2 from the chart on the previous page. Let's look at example 8. Find the horizontal asymptote of f of x is equal to x squared minus 3x plus 5 over x minus 1. So first you look at the degree of the numerator. That's 2. Then you look at the degree of the denominator. That's 1. When the degree of the numerator is larger than the degree of the denominator, you do not get a horizontal asymptote. So no horizontal asymptote. However, you do get what we call a slant asymptote, or some people call it an oblique asymptote. Oblique is a word that means slanted. You have several things in real life that talk about oblique. You have your oblique muscles. They're the slanted muscles in your abdomen. You have an obelisk. That is a monument or a statue that is slanted toward the top, like the Washington Monument. So oblique means slanted. Now, how do you find the slanted asymptote? Use long division. So we'll do that now. Or you can use synthetic division. Oops. This one, we can use synthetic division because the denominator is in the form of x minus 1. So we're going to go ahead and synthetically divide this out. So remember, when you use synthetic division, it has to be in the form of x minus c. So c is equal to 1, and c is the number that goes on the outside of the synthetic division box. We'll go ahead and put in the other coefficients. 1, -3, and 5. Synthetically divide, bring down the 1. 1 times 1 is 1. -3 plus 1 is -2. 1 times -2 is -2. Draw the remainder bar, and we get 3. The slant asymptote is the quotient. So reform the quotient here. It's 1x minus 2. And again, we'll see toward the end of the lecture how all of these parts play in together when we go to form the graph. But the slant asymptote for this one is x minus 2. Now what that means is as x goes to negative infinity or x goes to positive infinity, the graph of the function is going to approach not a single number, but it's going to approach that line, y equals x minus 2. So it's going to get closer and closer to that line as it goes out to infinity on both the left and the right. Let's look at example 9. Rational functions can cross the horizontal asymptote somewhere in the middle of the graph. Find the point where the rational function f of x is equal to x squared minus 3x minus 2 over x squared plus 1 crosses its horizontal asymptote. So first off, we need to identify what the horizontal asymptote is. We'll look at the degree of the numerator, and that's 2 because it's a quadratic on top. The denominator's degree is also 2 because a quadratic on the bottom. Since the degrees are the same, then that means the horizontal asymptote is y equals the ratio of the lead coefficients. We have a 1x squared on top and a 1x squared on the bottom. So that's 1 over 1, which is y equals 1. So this rational function has a horizontal asymptote of y equals 1. To find where this function crosses the horizontal asymptote, we're just simply going to set the rational function equal to the horizontal asymptote. So you set the rational function equal to the value of the horizontal asymptote, and then you solve the equation. And we've solved these types of equations before in chapter 1. Here I will cross multiply. We get x squared minus 3x minus 2. I'm going to cross the denominator over to the other side. That's going to be 1 times x squared plus 1. Multiplying by 1 doesn't change the expression. So we get x squared minus 3x minus 2 equals x squared plus 1. We have x squared on both sides, and they cancel. On the left side, I'll leave the negative 3x. On the right side, we'll take the negative 2 and move it over. It adds with the positive 1 and gives me positive 3. And so, simplifying and solving, we get x is equal to negative 1. So that means there is a point on the graph of this rational function that is negative 1, comma 1. It's the x-coordinate that we just solved for, and we know the y-coordinate because the horizontal asymptote was at y equals 1. All right, so now let's take everything that we've learned today and a couple of things from a few lessons ago and put it all together to learn how to graph rational functions. So first off, start off with a function in lowest terms. First, find the x and y intercepts. Second, find the vertical asymptotes if there are any. 3, find the end behavior, which is for rational functions in the form of a horizontal or a slant asymptote. 4, find where the graph crosses the horizontal or slant asymptote. And then 5, plot points in the intervals separated by the x-intercepts and the vertical asymptotes. This last step is going to tell us where in the graph things should be placed. Let's look at example 10. graph f of x is equal to 2x minus 6 over x plus 2. So step 1 is to find the intercepts. So to find the x-intercepts, now here's a trick that you can take with you. The x-intercepts are when y is equal to 0. If you set the rational function equal to 0, let me show you this. If you set the rational function equal to 0, the first step you take in solving the rational function is to cross multiply. When you cross multiply, the x plus 2 goes over to the right side and gets multiplied by 0. Multiplication by 0 wipes out the denominator. So what you're left with is 2x minus 6 equals 0. This will happen every time. Every time that you have a rational function that's just p over q. So the shortcut to finding the x-intercepts is just to start with the numerator equal to 0. You can't get any more information about the x-intercepts from using the denominator. So just set the numerator equal to 0 and then solve. So that's what I've done here on the left. 2x minus 6 equals 0. Solve that for x, and you get x equals 3. So that's 3 comma 0. Next, let me find the y-intercept. The y-intercept is when x is equal to 0. So we'll say f of 0, right? That's the notation for taking a value x equals 0 and plugging it into the function itself. F of 0 is 2 times 0 minus 6 over 0 plus 2. That's negative 6 over 2, which is negative 3. That gives me the point 0 comma negative 3. Step 3, sorry. This is technically step 1 still. Here is step 2, the vertical asymptotes. To find the vertical asymptote, set the denominator equal to 0 and solve for x. So we get x is equal to negative 2. Now step 3, find the horizontal asymptote. Find the horizontal asymptote. Take the degree of the numerator and the degree of the denominator. Both of those degrees are 1. So the horizontal asymptote is the ratio of the lead coefficients. That would be 2 over 1, which is 2. So the horizontal asymptote is y equals 2. Next, we want to find where the graph crosses its horizontal asymptote. So step 4, horizontal asymptote crossing. So we will take the rational function itself and set it equal to the horizontal asymptote. So we have 2x minus 6 over x plus 2 is equal to 2. Cross multiply. You get 2x minus 6 over x plus 2. We're going to cross multiply the x plus 2. So you get 2x minus 6 equals 2 times x plus 2. Distribute the 2 on the right side. Notice that the two x's, they cancel, and they leave only numbers, and then it's a matter of whether or not the numbers agree. You get negative 6 is equal to 4. That's not true. So this equation has no solution, which means there is no crossing point for the horizontal asymptote. So no solution here means no crossing. We'll use that information to help us graph this rational function at the end. All right, in step 5, I want you to watch very carefully. This is something completely new. What you do is you set up a number line. And what we're going to determine with this number line is where on the graph the pieces of this rational function go. We know that there are places where the graph naturally splits up. And those places are the x-intercepts and the vertical asymptotes. So we have a vertical asymptote at negative 2. I'm going to mark the number line above that with a VA to represent vertical asymptote. We have an x-intercept at x equals 3. I'm going to mark above that with a 0 because we know that the x-intercepts are the zeros of the function itself. So we're really sort of determining the y value from that part. Now there is a rule that says if you've identified all of these points, then whatever behavior this graph has at one point in this interval, then it has that behavior throughout that interval. So all I have to do is test a point in this interval, and that will tell me what that thing does throughout that interval. In other words, the places where the graph could change are these places that I have already marked. And so everything has to line up perfectly inside the intervals around that. You may hear people call these test points and things like that. So we're going to do some testing. And what you do is you pick a number between negative infinity and negative 2, and you run that through the function. I will pick negative 3. So we really want to know what the value of f of negative 3 is. And so I'll do this one time for you so you can see this. It's 2 times negative 3 minus 6 over negative 3 plus 2. You're literally just plugging in the test value into the original function itself. When you work this out, you get positive 12. It's not so much that the 12 is important, it's what the sign is. It's a positive. If the function is positive at negative 3, the function is going to be positive for every value from negative infinity up to negative 2. And we symbolize that by putting in a bunch of little positive signs right here. It says it's positive all along this interval from negative infinity up to negative 2. Now remember, these positives that we're putting in, those are y values. Next, we need to test a value between negative 2 and 3. I will pick 0. 0 is always usually a pretty good number to choose, especially since we've already figured that one up. That is the y-intercept, and it was negative 3. And so we know that that one is negative, and we'll fill up this interval with a bunch of negatives. And then f of 4, if you run that through the function, you get positive 1/3. and that's a positive. And so everything from 3 to infinity is positive. All right, let's put those together. I have to scroll down. You can continue to look at your page. Let's have a graph right here. And let's mark the x-intercept at x equals 3. Let's mark the y-intercept at y equals -3. We have a horizontal asymptote, vertical asymptote. Vertical asymptote at x equals -2. The vertical asymptote and the horizontal asymptote are represented by dashed lines. We have a horizontal asymptote at y equals 2. Now this is where it comes into play the piece of information we talked about before with x approaching a number from the left and the right and everything else. The number line from part 5 here tells me that information. We know that we have a vertical asymptote as x is equal to -2. As we go, x approaches -2 from the left, all of the y values are positive. That means the y values are going to approach positive infinity from the left. As x approaches -2 from the right, all of the y values are negative. So that means as x approaches -2 from the right, all of the y values are negative, and that goes to negative infinity. So we have to draw that now on our picture. As x goes toward -2 from the left, it approaches positive infinity. And as x approaches -2 from the right, it approaches negative infinity. So that is handling the vertical asymptote aspect of this graph. What was the end behavior? Well, we have a horizontal asymptote at y equals 2, and so we draw the graph as it approaches positive 2 going out to the left, and it's from above. Right. On the right side, we have a horizontal asymptote still at y equals 2, and it's from below. We know all the y values are positive, but more importantly, we know that it never crossed that, and we also know that we have to somehow get down to this point here and this point here. So now I'm just going to draw it, and it's going to go through there. And it's not pretty, because I'm not very good at drawing it, but that's what it should look like. It's really some sort of very smooth curve, if you get the perspective right. Let's look at example 11. Graph g of x is equal to x squared plus 3x minus 4 over x squared minus 2x minus 8. So first, let's find the x-intercepts. We find the x-intercepts by setting the numerator equal to 0. It's a quadratic, so you have to use one of your quadratic methods. Does it factor? If it doesn't, you can use the quadratic formula. This one factors. 4 splits up as 4 and 1. I need a positive 3, so I'm going to make the 4 positive and the 1 negative. Solving each of these equations, I get x is equal to negative 4 and x is equal to positive 1. And that gives me the points negative 4, 0, 1, 0. We also need to find the y-intercept, or y-intercept. And so that's going to be g of 0. Remember, to find the y-intercept, you evaluate the function at 0. So it would be 0 squared plus 3 times 0 minus 4 over 0 squared minus 2 times 0 minus 8. If you add all that up and divide, you get 1/2. And that gives me the point 0, 1/2. Next step, let's find the vertical asymptotes. To find the vertical asymptotes, set the denominator equal to 0. Again, you have a quadratic, so you have to factor or use the quadratic formula. This one factors. Eight factors as 4 and 2. We need to create a negative 2 in the middle term, so the 4 needs to be negative and the 2 needs to be positive. When you set each factor equal to 0, you get x equals 4 and x equals negative 2. Step 3, find the horizontal or oblique asymptote. To do that, we'll compare the degrees. So the degree of the numerator is 2. The degree of the denominator is also 2. Remember, the degree is the highest power on the x. When these are the same, we use the ratio of the lead coefficients. Both coefficients are 1, so it's y equals 1 over 1, which is y equals 1. So we have a horizontal asymptote at y equals 1. Next, we need to determine if this graph actually crosses its horizontal asymptote. To do that, take the rational function itself and set it equal to the numerical value of the horizontal asymptote, 1. Solve this equation by cross multiplying. So we get x squared plus 3x minus 4 is equal to 1 times x squared minus 2x minus 8. The x squareds cancel. Moving the x's to the left side, I get 5x moving the constants to the right side. Negative 4 plus 4 is minus 4. And we get x is equal to negative 4 over 5. That tells me that the graph is going to cross the horizontal asymptote at negative 4 over 5, comma 1. The 1 is the y value. It's at y equals 1, so the y value has to be 1. So it's negative 4 over 5, comma 1. And then step 5, let's do the sign chart. We have x-intercepts at negative 4 and 1. We have a vertical asymptote at 4 and negative 2. Now we're going to put indicators above these numbers to represent where they came from. So negative 4 was a 0. 1 is a 0. Negative 2 was a vertical asymptote, so I put a VA there. And 4 was also a vertical asymptote. We'll put another VA there as well. We know that the behavior of the rational function cannot change unless it passes through one of these x values. So let's test values inside each of these intervals. For the interval that goes from negative infinity to negative 4, I pick up the value negative 5. I've pre-worked all these. G of negative 5 is 2/9. And you get that value by plugging in that value into the original equation, into the original function. More importantly, this is a positive number. So we know that the rational function has positive values on the interval from negative infinity to negative 4. Next, I need to pick a value in the interval negative 4 to negative 2. So that would be g of negative 3. Again, I've pre-worked this. It's negative 4/7, and that's a negative. So we're going to have some negative function values between negative 4 and negative 2. Pick a number between negative 2 and 1. I pick 0. So g of 0 is 1/2. That's the y-intercept, and it's positive. G of 2 is negative 3/4, and it's negative. And G of 5 is 36/7, and it's positive. All right, so these values here, these are the values that I use to generate the sign chart above it. I'm going to erase those so that I can have space to draw the graph. And now let's put in the graph. Negative 2, negative 4, 1, 2, 3, 4, and 5. So we have a vertical asymptote at x equals negative 2 and x equals positive 4. We have a 0 at x equals negative 4 and x equals 1. We have a horizontal asymptote at y equals 1. We have a y-intercept at 1/2. So there was y equals 1, so 1/2 is smack dab in the middle. We have a point where the graph crosses the horizontal asymptote at negative 4/5. I'm going to put that right there. All right, now we use the sign chart to graph where the branches of the graph actually occur. If I use this first interval, it says that the graph is going to be positive from negative infinity to negative 4. We know that it has to approach y equals 1. And we also know that it's going to be negative between negative 4 and negative 2. So that means as it approaches the vertical asymptote at x equals negative 2, there's going to be some negative values. So it's going to have to be down here. The question is, why couldn't it be up here? Well, the answer lies in these negatives here. If the graph were to come in up here, then it would have to cross the horizontal asymptote in order to get close to the vertical asymptote going on the negative side. Since there are no more crossings of the horizontal asymptote, it can't possibly do that. So it must be coming into the horizontal asymptote from below, and then it continues on toward the vertical asymptote, and it's negative. As x gets closer to negative 2, but from the right side, we see that we have positive values getting closer to the vertical asymptote. So that's up here. It's going to pass through all of these points. We have a 0 here at 1, and then it's negative, and it gets closer to that vertical asymptote. And then, as x approaches 4 from the right, the values are positive. And as x goes to infinity, the graph approaches y equals 1. Let's look at example 12. Graph h of x is equal to 2x squared minus 2 over x minus 3. So we repeat these same steps. Part 1, find the x-intercepts. So we'll take the numerator, set it equal to 0. First, notice that you can factor out a 2, and that gives us 2 times x squared minus 1. X squared minus 1 factors as 2 times x minus 1 times x plus 1. Then set each factor equal to 0. Now the 2 doesn't have an x, So you would technically get 2 equals 0, which does not give you a solution. 2 does not equal 0. But the other two do. You get x equals 1 and x equals negative 1. So the x-intercepts are 1, 0 and negative 1, 0. Next, we want to find the y-intercept. So h of 0 is 2 times 0 squared minus 2 over 0 minus 3 so that's going to be 2/3. Step 2, find the vertical asymptote by setting the denominator equal to 0. And that gives you x equals 3. Step 3. We need to find the end behavior. The degree of the numerator is 2. The degree of the denominator is 1. Because the degree of the numerator is 1 larger than the degree of the denominator, that's going to result in a slant asymptote. To find the slant asymptote, we're going to use synthetic division. The numerator is 2x squared plus 0x minus 2. And we're going to divide that by x minus 3. Now remember, you can only use synthetic division if you are dividing by a linear factor that has a lead coefficient of 1. So this one is perfect. You may experience other ones where you are required to do long division. You just have to do long division on certain ones. Let's divide. Bring down the 2. 3 times 2 is 6. 6 plus 0 is 6. 3 times 6 is 18. 18 minus 2 is 16. The slant asymptote is the quotient from this division. The quotient is this piece right here, so it's y equals 2x plus 6. Step 4, let's determine if the function itself crosses the slant asymptote. To do that, we will take the rational expression and set it equal to the slant asymptote. So we get 2x squared minus 2 divided by x minus 3 times or equals to 2x plus 6. To solve this equation, cross multiply, and you get 2x squared minus 2 equals 2x plus 6 times x plus 3, x minus 3. Multiply out the right side, you get 2x squared minus 6x plus 6x minus 18. Notice what cancels. 2x squared cancels. 6 x's cancel, and we're left with no x's. That's not good. That leaves us with the equation negative 2 is equal to negative 18, which is not true. So there's no solution to this equation, and there is no crossing. Finally, let's create the sign chart. We have x-intercepts at negative 1 and positive 1. And we have a vertical asymptote at x equals 3. So again, you would test each of these inside the interval. So h of negative 2 is negative 6/5. That's negative. H of 0 is 2/3. And that's positive. H of 2 is negative 6. That's negative. And h of 4 is equal to 30. That's a positive. So again, we have the sign chart. The sign chart is going to tell us where the pieces of the graph go. With this information, we can draw the graph. Let me draw the asymptotes first. We have an asymptote at x equals 3. I'm going to draw this in green. Next, we have a slant asymptote on the line y equals 2x plus 6. So that's going to start at 6, and it's going to go up 2 for everyone. I should mention that these are by 2s. I had to scale this properly here. So here's 6, and it goes up by 2 over 1. So it's going to be this asymptote here. Oops. So it is a slant asymptote. It has a slope. It's positive 2, and it starts at y equals 6. From there, we can put in the other pieces of information. We have an x-intercept at negative 1 and at positive 1. We have a y-intercept at 2/3. I'm going to put it right there. And that's it. As x approaches 3 from the left, all the values are negative, so it goes down to there. As x approaches 3 from the right, all the values are positive. You can see that on the sign chart right here. As x approaches 3 from the right, all the values are positive. And it just whips around like that. The end behavior for this graph is y equals 2x plus 6. So as the x's get closer and closer to negative infinity, the line gets closer and closer to y equals 2x plus 6, going out to the left. As the x's get larger and larger. X goes to positive infinity. It gets closer and closer to y equals 2x plus 6. Does it ever hit y? Does it ever hit this slant asymptote as it goes out further this way, or does it go out further to the left? Does it ever hit that? The answer is no, and that's because it didn't have a slant crossing.